and today I'm gonna discuss VRF system additional refrigerant charge calculation. So there I have prepared an Excel sheet to show you the calculation for additional refrigerant needed for your system. If you remember that last time I have used this software VRF selection tool to design and draw our system, and we have made the PDF file also in the form of results. So our machines like outdoor units and indoor units, these indoor units and outdoor units are pre-charged from the factory, so their refrigerant is already calculated there, but we want to calculate the additional refrigerant due to the piping which we have draw over here. So right now I'm gonna calculate the additional refrigerant due to this piping, because indoor units, outdoor units already pre-charged from the factory. So let's start the calculation. Here I have an Excel sheet. So there I'm gonna use two tables for refrigerant charge calculation, and here is the formula which I already applied here to calculate the additional refrigerant. So this first table is you can see over there, dia is mentioned 6.4, 9.5, 12.7, 15.9, 19 and 22 mm. So, and this is the additional refrigerant needed per meter length due to 6.4 mm dia. So 0.025 kg additional refrigerant is needed per meter length of the pipe due to 6.4 mm dia. So all of these lengths are mentioned per meter. Per meter we need 0.055 kg additional refrigerant due to 9.5 mm dia. So in the same way 0.35 kg refrigerant is needed per meter of dia 22.2 mm. So this is the formula which I am gonna use to calculate additional refrigerant, that is L1 into this additional refrigerant 0.025, because this is due to dia 6.4, and then L2, this is L2, and L2 into additional refrigerant needed is 0.055. so this is the values which I will give over here: L1, L2, L3, L4, L5 and L6. These are the real lengths. As you can see over here, real total length of the pipe dia 6.4 mm, real length of the pipe dia 9.5 mm, and till L6, that is real total length of liquid pipe dia 22 mm. So these are the calculation we have to perform for liquid side, not for the gas side. So that's why it's written that real total length of liquid pipe dia 22 mm, L6 length. So all of the lengths we will provide over here, whatever the lengths which we have used over here, real lengths in our software. So I'm gonna use these lengths over here. So L1, which we will provide over here, into 0.025 kg of the additional refrigerant needed per meter. So in the same way, that is L5, this is our L5, L1, L2, L3, L4 and L5. So L5, how much refrigerant do we need over here? That is 0.25 kg per meter due to dia 19 mm. So, and one more thing in this formula is we need to add additional refrigerant to the system compensation, system horsepower compensation. As you can see over here, this formula, as you already understand. And second thing, you have to add the compensation by system horsepower. So this value will take from these tables. This is the compensation due to the horsepower of the system outdoor unit which we have selected. This is for the standard efficiency models, and this is for the high efficiency models. So whatever the value of your outdoor unit horsepower, let's say our outdoor unit horsepower is 14, and additional refrigerant needed due to the 14 horsepower outdoor unit is 8.5 kg. So we need to add this one also here. So let's move back to our software, and if you remember that I have made PDF files in my last video to interpret the data. So I'm gonna open this table. So as you can see that when we were making our VRF system design in my last video, I have created a PDF file from our design. So we know that the outdoor unit capacity which we have calculated over here is 26 horsepower, and we use two outdoor unit. As you can see over here, there are two outdoor unit. One is 14 horsepower and the second is 12 horsepower, total 26 horsepower. And as you can see that through the software we have calculated 14.7 kg additional refrigerant. So I will compare this value with the value in my Excel sheet. So I'm gonna, let's go back here, and you can see that this is all the diameters which we have used in our project. And you have to know one thing. This first one is for gas. These are the real lengths in meter, and the first one is for the gas pipe and second one is for the liquid. Same, first one for the gas, second for liquid. First for gas, second for liquid, and this is the total length for 3/8 including gas and liquid size, that is 27.4. half inches for gas and liquid both, that is 38. So we are going to use the liquid side lengths. So first we have dia 1/4. 1/4 dia is nothing but it's 6.4 mm. So this is our length L1. So what is the length L1? 1/4 is 6.4 mm. So liquid size, as you can see that 32 meter is the length, this length in meter. So 32 meter is the length which we have used here. So I'm gonna give 32 meter length here. And now second is 9.5 mm. As you can see, 3/8 inches is 9.5 mm. If you convert this in inches to mm, it will be 9.5 mm. So how as you can see, the length which we have gas side is 7.5. Since we are using the liquid side, so it's 19.9 mm, 19.9 meter, sorry, not mm, 19.9 meter due to 9.5 mm diameter. How much length? 19.9 meter. So 19.9 meter. Now I'm going to take the third length, that is half inches. Half inch is nothing but it's 12.7 mm, as you can see over here. And here it's half inches, and first one is for the gas, second is for liquid. So liquid size, how much is the length? That is 13.5 meter due to half inches, that is 12.7 mm dia, 13.5 meter length. And now go to L4. L4 is due to the dia 15.9 mm. 15.9 mm is same as 5/8 inches. If you convert this in mm, it will be 15.9 mm. So 5/8. How much is the length on the liquid size? That is total is 28.8. Gas side is 19.9 meter, which we have and you know that these lengths which we have calculated from this project which we have created before in my last video. So every data is in the table form which we have created in last video. So now this is L4 due to the dia 15.9, that is 5/8 inches. So liquid size, liquid side length is 8.9 meters. You can see over here 8.9 meter. So 8.9 meter. and L5 is the length due to the dia 19 mm. 19 mm. 19 mm is nothing but it's 3 by 4 inches. As you can see that gas side there's no length, that is 0. We did not use any dia 3 by 4 for the gas, but for liquid it's 6 meters length we have used for 3 by 4 inches, so 6 meter. And the last one is L6. L6 is due to the diameter 22.2 mm, and if you convert this into inches, 22.2, it will be 7 by 8, and as 7 by 8 inches, 22.2 is 7 by 8 inches. As you can see that gas side we have 10.8 and liquid side is 0, so we did not use any liquid pipe with 7 by 8 inch, so this length is 0 used in our project. So I'm gonna give this one as 0. So as you see that I have provided all the lengths, and I have applied the formula over here, all lengths we have. Let me tell you again, this L1, the formula which we have used here is, that is length L1 due to the dia 6.4, because this is the real length of liquid pipe, dia 6.4. This is 32 meters. As you know that per meter due to the dia 6.4, how much additional refrigerant charge is needed? 0.025 kg. So we have 32 meters, so 32 into 0.025, you will get the additional refrigerant needed due to the dia 6.4 having length 32 meters. So in the same way, length L3, that is 13.5 meter used here, and this is the additional refrigerant needed 0.105 per meter, 0.105 kg per meter length of dia 12.7. Since we have 13.5 meter used in our project, so 13.5 into 0.105, so this will give you the additional refrigerant charge needed due to the dia 12.7 mm having length 13.5 meters. So all of this you have to add, and then in the last, as I told you, you have to add the compensation by the horsepower of the system. So since we have if you go over there and you will see we have selected 26 horsepower system here. As you can see over here, outdoor unit is 26 horsepower, and it's break down into two outdoor units, that is 14 horsepower and 12 horsepower. And you know that this is the standard efficiency model we have used, not a high efficiency model. So this is the standard efficiency model table, and outdoor unit which we have used over here is 26 horsepower, and you know that it's 14 and 12 break down into two outdoor unit, and you see that compensation by the horsepower is 8.5. so this 8.5 you need to add over here to get the additional refrigerant needed for your piping. As you can see that I have added this G17. G17 is this value due to the system horsepower, 8.5 kg additional refrigerant needed. So you can see over here the additional refrigerant needed is 14.7 kg, which we have calculated over here. And if you go over there from our software, we have calculated here is additional refrigerant is 14.76 kg additional refrigerant, 14.7. so here also 14.7. so we just compared this one with the software result. So this is how you can calculate the additional refrigerant needed for your system. Today I'm going to explain you guys about the expansion tank sizing procedure. So before starting the calculation, I want to explain you guys about expansion tank, what is expansion tank, and why we are using expansion tank in our system. So expansion tanks are basically required in a closed loop heating or chilled water system to absorb the expanding fluid and limit the pressure within the heating or cooling system. So it is important to properly size your expansion tank because a properly sized expansion tank will accommodate the expansion of system flow during the heating or cooling cycle without allowing the system to exceed the critical pressures. Also, expansion tank basically uses the compressor to maintain the system pressure by accepting and expelling the changing volume of water as it heats and cools. So this is the chiller yard drawing I have over here. As you can see, let me zoom it. This is the expansion tank that is connected to our system or pressurization pump set. As you can see here, this is expansion tank. So basically today we are going to do the expansion tank sizing, and in the end I will explain you guys about the position or location of the expansion tank where we need to put our expansion tank. So make sure to watch the video till the end to get a better understanding of the expansion tank sizing. So let's start moving to the calculation procedure of the expansion tank. I have made this Excel sheet. First of all, we have this sheet that is related to expansion tank sizing formula. Second one is basically related to system volume calculation, and the third one I have prepared over here for different charts and tables we are going to use during our calculations. So let's start this expansion tank sizing. So this is the formula which we are going to use to calculate the expansion tank size. So what is this formula? Let's look at this. Vt is equal to Vs into V2 divided by V1 minus 1 minus 3 alpha delta T divided by 1 minus P1 by P2. So what are these parameters in this formula? First we need to understand what are these parameters. Only then we are able to calculate the size of expansion tank. So what is Vt? Vt is basically the volume of the expansion tank, which we are going to calculate in gallons or cubic feet or cubic meter, and Vs is the volume of the system. Volume of the system means that all the pipes which we have used in our project, all of the volume occupied by the pipes and equipments, everything, it is the sum of all of the pipes and equipments volume. So we will calculate this one. And V1 is the specific volume of the water at low temperature, and V2 is the specific volume of the water at high temperature. And this P1 is low pressure, and the minimum pressure we took over here is 20 psi, the minimum pressure we can take for our system. And P2 is the higher pressure. Alpha is the linear coefficient of thermal expansion. It depends on material. This alpha value depends on material. Which material you are going to use, you need to put the value over here. So let me go to the third tab, that is tables and chart, to show you the value of alpha, that is linear coefficient of thermal expansion. So as you can see over here, there I have a material list for aluminium, carbon steel, cast iron, copper, and this is the thermal expansion coefficient for all the materials. So since we are working on chilled water system and the material which we use over here is carbon steel, so alpha value over here is 6.5 into 10 to the power minus 6 inches per inches degrees Fahrenheit. So this value we are going to use in our calculation because we are using black carbon steel material. So 6.5 into 10 to the power minus 6. So this is the value which I have used over here for the alpha. And delta T is equal to higher temperature minus lower temperature difference, and this is 66 degrees Fahrenheit. T1 is the lower temperature, T2 is the higher temperature. Now what is lower temperature? T1. T1 is basically our chilled water supply temperature, that is 44 degrees Fahrenheit. And T2 is the higher temperature or our ambient temperature on the location which I am working on. Let's say the location ambient temperature is 110 degrees Fahrenheit in which I am working with. So and T1 is the chilled water supply temperature. So delta T is equal to T2 minus T1. So our temperature difference will be delta T equal to this T2 minus T1, ambient temperature minus chilled water supply temperature. That comes out to be 66 degrees Fahrenheit. So now we have to calculate volume P1, specific volume of the water at lower temperature. Now how this value comes out, I will show you. So we know that our lower temperature till water supply temperature is 44 degrees Fahrenheit. Now we have to calculate the specific volume of the water at this lower temperature. So let's move back to our tables and chart to get this value. So 44 degrees Fahrenheit. So this table is in degrees Celsius and this one in Fahrenheit. As we know that our temperature is 44 degrees Fahrenheit, since we don't have 44 here, we have 40 and 50, and specific volume is same, 0.01602 at 40 degrees Fahrenheit and 0.01602 at 50 degrees Fahrenheit. So we can take this value at 44 degrees Fahrenheit, that is 0.01602 cubic feet per lb. So at 44 degrees Fahrenheit we have a specific volume of 0.01602 cubic feet per lb, and the specific volume of the water at higher temperature, and higher temperature ambient temperature is 110 degrees Fahrenheit. So move back to our table and chart again. As you can see that there is 110 degrees Fahrenheit, and specific volume of the water over here is 0.01617. so we can use this value 0.0167 cubic feet per lb at 110 degrees Fahrenheit. So this is value which I have right over here. So now we have to calculate the high pressure, that is 45 psi. How this comes out? P2 is basically our system maximum pressure. System maximum pressure is basically the pump head loss, which we have already calculated. If you have seen my previous videos related to chilled water pump head calculation, you can calculate the pump head and you can use that value over here to calculate your expansion tank size. So let's say the pump head which we have calculated over here is 70 feet. So we need to convert this into PSI. In order to convert this into PSI, you need to multiply this chilled water pump head with 0.433, and you need to add 14.7 in order to convert this absolute to the gauge pressure. So total formula is this pump head into 0.433 plus 14.7. So P2 is a higher pressure. Higher pressure we got over here is 45.01 psi. So now we have everything except system volume we will calculate now. So now we have V2, V1, we have alpha value for the material, that is black carbon steel 0.000065, and we know the pressure P1, minimum pressure of our system is 20 psi and the high pressure is 45 psi. So only thing remaining over here is volume of the system, Vs. So let's move back to our second tab in order to calculate the volume of water in system. I have divided this into two parts. First part is related to the pipes, all of the pipes which we used in our project, and second part is related to the equipment side, water content. So first part, so let's say that this is all of the pipes which I have used in my project. I have to write over here. I need to mention the lengths which I have used in my system. Let's say that I have write everything, and the third tab is related to weight of water in pipe, that is lb per feet. How much lb per feet is required for that much this pipe size. So let's say we have a 2-inch pipe, and move to the right side. This is the water content table which we are going to use. We can say that 2-inch pipe size, how much lb per feet of the water is required. 2 feet, this is the weight in lb per feet. 2 inches weight per lb per feet, how much weight is required, that is 1.36. So as you can see that 1.36 is required for 2-inch pipe size. And let's say 8-inch, how much weight of the volume is required. 8 inches weight of the lb per feet, that is 21.8. 21.8. So you have to write everything in the same way I have explained over here, that is lb per feet is required for each and every pipe, and the fourth column is related to water volume in gallons per feet. So let's say we have 3-inch pipe size. How much gallons per feet is required for 3-inch pipe dia? So gallons per feet for 3-inch pipe dia is required 0.367. You can see 0.367. So in the same way, let's say for 10-inch pipe size, how much gallons per feet is required for 10 inches? 10 inches gallons per feet 4.08. So in the same way, you have to write gallons per feet for every pipe used in your project. Now next column is related to total volume. As you can see that we have write volume of water in gallons per feet. So now we have 100 feet. 100 feet, we need to multiply this 100 feet with that much volume of water per feet. So we'll get the total volume in that much length. So as you can see, so we need to, as you can see, the formula which I have applied over here is the volume of the water in gallons per feet multiply this length. You will get the total volume in gallons within this pipe and this length. So total volume of the water required for 1/4 pipe size having 100 feet length is 6.4 gallons. So 4-inch pipe size is 73 feet length requires 47.67 gallons. So in the same way you have to calculate for all. So let's say we have calculated for all of these and we have summed it up over here. So we have summed it up and total volume of the water in the pipes is 1189.54 gallons needed. So this is basically the volume of the water inside the pipes which we have calculated over here. Now the second part is related to the equipment's volume. How much volume of the water will be inside the equipments. So let's say we have we have write everything which we have in our project: 4 air cooled chillers and air handling units, and then FCUs over here. So air cooled chillers we use in project is 4. So water volume in the gallons required per air cooled chiller is 18.5 gallons. You can get this value from the supply directly. So you can write over here 18.5 or whatever the value which you have for your chiller. So one chiller required 18.5, so 4 chillers required 74 gallons. So now the second we have air handling unit. So now we have air handling unit. So we need to write the water content in kgs and cubic meter, and then we need to convert this into gallons to get the total volume in gallons. So let's say we have air handling unit with a water content of 24.89 kgs. You need to convert this into cubic meter by dividing by 1000. So next is we need to convert this into gallons. You can get this value also from supply, how much content of the water is required for your air handling unit. So water volume in the gallons, in order to convert this into gallons, you need to multiply this cubic meter with 264.172 in order to convert this into, because 1 cubic meter required 264.172 US gallons. So this air handling unit requires 6.58 US gallons. So since we have one air handling unit of this type, so we got total volume is 6.58 gallons. So in the same way you have to calculate for all of the equipments of your project. So in order to get this value and then you have to sum up all the volume of the system which you have calculated above. So total volume of the equipment over here is 140.94 gallons. So for the due to the pipe, the volume which we have calculated is 1189.54, and due to the equipment, the volume which we have calculated over here is 140.94 gallons. So total volume of the system is equal to pipe volume plus equipment volume. So pipe volume is equal to 1189 and the equipment volume is 140.94. So this comes out to be 1330 gallons. So now we have to apply safety factor. You can take safety factor 10 to 15%. So now I am going to apply 10% safety factor to our calculation. So 10% safety factor of 1330 will be 133 gallons. So total volume of our system will be now 1400, that is 1330 plus 133, that is equal to 1463.53 gallons. So now what you have to do, you know all the values. You know V2, you know V1, you know alpha, delta T, P1, P2 and Vs, total volume of the system we have just calculated now, that is 1463.53 gallons. So now we have to put all the values in our formula over here, that is Vs into V2 by V1 minus 1 minus 3 alpha delta T divided by 1 minus T1 by T2. So I have already write the formula over here and put all the values over here. After that I got the value is 24.66 gallons. So round off it will be 25 gallons. So for that much system volume, 1463 gallons volume of the whole system, how much size of the tank it should be? It should be 25 US gallons. So our expansion tank size should be 25 US gallons. So this is how you can calculate the expansion tank size. So it's very easy to calculate. If you know all these values, you have to put it and then you can get the expansion tank size. And the last thing I want to explain over here is the location related to the expansion tank. So about the location of the expansion tank, since the point of connection of expansion tank to system is point of no pressure change, therefore it is typically located at the suction side of system pumps. As you can see in this drawing, this is our expansion tank and this is our main chilled water return header, and this expansion tank is connected to main chilled water header, and this is further connected to suction side of primary chilled water pump. Therefore our expansion tank is connected to suction side of primary chilled water pumps, and we don't want any air to withdrawn into the system, and we want the pressure everywhere in the system must be above atmospheric pressure, and we don't want any air to drawn into the system. That's why it is located on the suction side of the pumps. So I hope you guys learned something from this video. Now you guys can calculate easily expansion tank size, and for more videos keep watching my channel and don't forget to subscribe.